Let us continue our discussion on the various thermodynamic properties and their relation. And in this lecture, we will discuss on the relationship between Cp and Cv. See, usually we say that Cp minus Cv is equal to Nr, but Cp minus Cv equal to Nr is only applicable to perfect gases. And when the gases are not perfect, then Cp minus Cv is not equal to Nr, but it is modified. It is different than Nr. And moreover, this Cp and Cv are not just the thermodynamic quantities for the gases. Cp and Cv can be defined or measured for a substance in any of its phase, be it solid, liquid or vapor. So today we will develop thermodynamic relations between Cp and Cv which are applicable to all the systems. Let us first begin with a general definition of Cp and Cv. Cp minus Cv, let us write down for Cp minus Cv. This is equal to Cp is dou H dou T at constant pressure and Cv is dou U dou T at constant volume. This I have substituted the exact definitions of Cp and Cv. Now you know that H is equal to U plus Pv. So Cp minus Cv gets modified to, let us take its derivative with at constant pressure. This will be dou U dou T at constant pressure plus P dou V dou T at constant pressure. This is just the differentiation of H, that is for dou H by dou T at constant P, minus dou U dou T at constant volume. What I have here is Cp minus Cv is equal to variation of internal energy with respect to temperature at constant pressure minus variation of internal energy with respect to temperature at constant volume, this and this I have combined, plus P into variation of volume with respect to temperature at constant pressure. We have just discussed that du, if in the previous session, du is equal to dou U dou T at constant volume dt plus dou U dou V at constant temperature dV. We just discussed that. And from this, I can write variation of internal energy with respect to temperature at constant pressure is equal to variation of internal energy with respect to temperature at constant volume plus variation of internal energy with respect to volume at constant temperature into variation of volume with respect to temperature at constant pressure. I have divided throughout by dt at constant pressure. The reason is why I have done this, because I am interested in substitution for this, which I can get from this. I can substitute over here. So I will use this in the next slide. What I will get is Cp minus Cv, and for that difference it will be dou U dou V at constant temperature into dou V by dou T at constant pressure plus P into variation of volume by temperature at constant pressure. So, what I have is Cp minus Cv is equal to, I take this as common, variation of internal energy with respect to volume at constant temperature plus P into variation of volume with temperature at constant pressure. See, what I have done is, we have not so far used any condition for ideality. That means the equation that we have developed between Cp for Cp minus Cv is applicable to all the systems. It is not just applicable to the ideal gases, but it is applicable to all the systems. It allows for the deviations from ideality. Now, from this equation, I can further derive two equations. Let us say for ideal gas, the variation of internal energy with volume at constant temperature is going to be 0. So, if I substitute 0 over here, I have Cp minus Cv is equal to P into variation of volume with temperature at constant pressure. Now you remember that PV is equal to nRT. This is for ideal gas. So according to this, P into variation of volume with respect to temperature at constant pressure is going to be nR. Derivative of volume with respect to temperature, here temperature derivative with respect to temperature is 1, so we have nR. And this I can substitute over here. Once you substitute over here, you get Cp minus Cv is equal to nR. This is the equation that is applicable to ideal gas. And this is the most widely given answer when someone is asked, what is Cp minus Cv? For ideal gases, it is equal to nR. Now, let us keep this equation in mind. I will rewrite this equation and will show you that how it takes up another form. So, we will come back to this equation, but before that, let us look at some very useful mathematical relations. This relation we have been using so far, that if z is a function of x and y, then any variation in z, that is the differentiable function z, dz is equal to dou z dou x at constant y dx plus dou z dou y at constant x dy. This we have been using. Another relation that we will be using now in solving the further questions is Euler chain relation. This is sometimes also called chain relation, or this is also sometimes called cyclic rule. That is, for any differentiable function z, which is a function of x and y, dou y dou x at constant z into dou x dou z at constant y into dou z dou y at constant x is equal to -1. This is a cyclic rule because you are just making a cycle between y, x and z. So you see, note down here, dou y dou x at constant z, then we shifted to dou x dou z at constant y, you see here, and then we shifted to dou z dou y at constant x. See here, this has to be equal to -1. Keep that in mind. And one more relation, that is the reciprocal identity that we will be using. Dou y by dou x at constant z is equal to 1 over, you take a reciprocal of this, dou x by dou y at constant z. So these mathematical equalities or these mathematical equations will hold, and we will make use of these relations in solving further numerical problems. Let us now take up one by one. Question number 1, show that dou u by dou t at constant pressure is dou u dou t at constant volume plus dou u dou v at constant temperature into dou v dou t at constant pressure. We have just discussed this at length. Therefore, we will switch over to the next question, is to show that the difference between Cp and Cv is equal to T times dou V dou T at constant pressure into dou P dou T at constant volume. So the best way to attempt these type of questions or to solve these kind of questions is that we actually start with the definition of Cp and definition of Cv and proceed. Now let me again come back to the same equation that we just derived. I will use this equation and proceed from here to get an answer to question number 2 that is being asked. So let me rewrite this equation on a different slide. What we have is Cp minus Cv is equal to variation of internal energy with volume at constant temperature plus pressure into variation of volume with temperature at constant pressure. And if you look at the slide, question number 2, the variation of volume with temperature at constant pressure is already there in the answer. But in the answer, there is no separate pressure term, although derivative is there. Therefore, when we look at this slide, this expression, we need to get rid of pressure. So the strategy should be that we find out an expression which we substitute in this, and that should allow us to get rid of the pressure. How we can proceed? Can we write an expression for the dou u by dou v at constant temperature? And that should allow us to get rid of pressure. Let us think. Maybe this equation du is equal to Tds minus Pdv. This is a fundamental equation. You see, this equation can allow us to express variation of internal energy with respect to volume at constant temperature, and pressure will also appear in this. So if I divide throughout by V at constant T, what I will get is T variation of entropy with volume at constant T minus P. And if I substitute this over here, I will get rid of P. What do I get now? Cp minus Cv is equal to T variation of entropy with volume at constant temperature minus P plus P, and what I have is variation of volume with temperature at constant pressure. So what I have, Cp minus Cv is equal to T into delta S delta V at constant temperature into delta V and delta T at constant pressure. Now if we look at the question number 2, we have arrived at a relationship which is closer to what is required, but we do not have in the final answer variation of entropy with volume at constant temperature, but what we have is here the variation of pressure with respect to temperature at constant volume. So therefore we need to convert or write another derivative which is equivalent to this and should be able to connect pressure and temperature. And here we will use one of those Maxwell relations. What are those Maxwell relations? We have discussed earlier. That is, you remember that if you start with A is equal to U minus Ts and dA is equal to this, we have discussed earlier many times, du minus Tds minus SDT, or dA instead of du, if I write du is equal to Tds minus Pdv, this is du, minus Tds minus SDT, this and this get cancelled. So what I have is dA is equal to minus Pdv minus SDT. This will allow me to write a Maxwell relation, that is dou P by dou T at constant volume is equal to variation of internal energy with volume at constant temperature. And that's what I was looking for, that can I connect this variation of entropy with volume at constant temperature with pressure, temperature and volume. So what I had earlier was Cp minus Cv is equal to temperature into variation of entropy with volume at constant temperature, variation of volume with temperature at constant pressure, and I will substitute this. What I have is T into variation of pressure with temperature at constant volume, variation of volume with temperature at constant pressure. This is what was asked. Look at in the slide the question number 2. Cp minus Cv is equal to temperature into dV by dt at constant pressure, dP by dt at constant volume. So we have here proved that this relation holds true. Please remember again that the equation that we have derived is not just applicable to ideal equation. It is applicable to all the systems. What we need to know, how the various thermodynamic properties depend upon volume, depend upon pressure, depend upon temperature. And this equation number 2 that we derived, you can yourself show that for ideal gas this will convert equal to Nr. If you just find out for ideal gas what is this variation of volume with temperature at constant pressure and the variation of pressure with temperature at constant volume, you will find out that Cp minus Cv for ideal gas turns out to be equal to Nr. Now, the question number 3 is to show that Cp minus Cv is equal to V times T into alpha square over isothermal compressibility, Kt. So, we can use this equation, the equation that we derived, to get this result. Let us see how do we do that. The equation that we derived is Cp minus Cv is equal to temperature into variation of volume with temperature at constant pressure into variation of pressure with temperature at constant volume. Variation of volume with respect to temperature at constant pressure, you remember that earlier I introduced expansion coefficient alpha, which is 1 over V into dou V dou T at constant pressure. This is expansion coefficient. And isothermal compressibility, Kt, isothermal compressibility is equal to minus 1 by T into how the volume responds to pressure at constant temperature. See, this was expansion coefficient, this is compressibility, and isothermal, I am putting that is by T. But in this equation, I don't have Vpt. You see here PTV and Vpt, and that reminds us that we can use the cyclic rule. That means, if I use this P, T, V, T, V, P, V, P, T equal to minus 1, this is a cyclic rule. This will allow me to write for variation of pressure with respect to temperature at constant volume is equal to what do I write? Minus variation of volume with respect to temperature at constant pressure divided by variation of volume with respect to pressure at constant temperature. You see, this when I am taking on the other side, I am using the inverse relation VTP, and this I am taking directly in the denominator. So, this allows me to write dou P by dou T at constant volume is equal to minus this, if I use this, this is equal to alpha times V, and this if I use from here, which is equal to minus Kt times, I am sorry, let me correct over here, this has to be per unit volume, not temperature, per unit volume, please correct this. Variation of volume per unit volume into what I have here is volume. So this is equal to alpha over kT. And now if I substitute over here, what I have? T. For this I will use alpha V for this, delta V by delta T at constant pressure is alpha V, into I have alpha by kT, which is equal to alpha square T V by kT. This is what was asked from us. Now let us take a look at another question. Suppose S is regarded as a function of P and T, then show that TdS is equal to Cp dt minus alpha Tv dP. Let us see how we use the given information to come up with the answer. We are asked to treat S depends on P and T. So immediately I will write ds is equal to variation of entropy with respect to pressure at constant temperature dP plus variation of entropy with temperature at constant pressure dt. In the given question, along with the dt term, there is a Cp. How do we get Cp? I can get, you know that dq at constant pressure is equal to, dq is always equal to Tds, and constant pressure means I will say dH. So from this equation, can I write dou H by dou T at constant pressure is equal to T into ds by dt at constant pressure, right? And this is nothing, this is Cp. So I can substitute now here. Let us multiply T on each side. Tds is equal to T times dou S dou P at constant temperature dP plus T times dou S dou T at constant pressure dt. Now I can use this information over here, and I have Tds is equal to T into dou S dou P at constant temperature dP plus Cp dt. So at least one part we have been able to get as asked in the question. Cp dt is there. Now we need to get the other part, and in order to get the other part, we can again use the Maxwell relation. And what we need now is the variation of entropy with pressure, and for that we can use again another Maxwell relation from dg is equal to V dP minus STT, because this will allow me to express the variation of entropy with respect to pressure at constant temperature. According to this, the variation of entropy with pressure at constant temperature is minus variation of volume with temperature at constant pressure. And is it not equal to minus alpha times V, because I have already discussed that what is alpha? Alpha is 1 over V dou V dou T at constant pressure. This is equal to minus alpha V. So now if I substitute in the equation that we just derived, that TdS is equal to Cp dt plus T into 2S dou P T dP, that was the equation that we just derived in the previous slide, and for this dou S dou P dou at constant temperature I will put alpha V. So I end up with TdS is equal to Cp dt minus alpha Tv into Tp. This was the required answer. Now you can integrate and calculate the changes in entropy when the other properties of the system are known. So this kind of equations allow us to account for the deviations from ideality. Please remember again that in deriving these equations we have not assumed any ideal behavior. And for example, this particular equation will allow you to calculate the entropy changes when the temperature changes and pressure changes. So what information do we need on the systems then? Is the heat capacity, expansivity, the temperature and volume. Similarly, we can get another equation in terms of Cv, and this you can try yourself. The approach will be exactly the same. Only thing is, in place of constant pressure, you will be using constant volume condition. So what we have discussed in this particular lecture is that the various thermodynamic properties which are not just applicable to ideal systems. The differences, for example, in Cp and Cv can be expressed in many forms, and what we have to look for is that we should express this in a form which result into the thermodynamic properties which can be experimentally determined. And these equations allow deviations from ideality, and once you use the rules for ideal gases or ideal solutions, you will see that these various equations will take up the form which we have earlier derived for ideal gases or ideal solutions. Thank you very much.